Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. In this video, we are going to analyze Truss, indeterminate Truss, and I want to explain how we want to include the effect. The effect in Truss, we call it as temperature changes and fabrication error. We will use the example given yesterday. We will continue to calculate the reaction, the redundant reaction as well as member forces. Considering temperature changes and fabrication error. Okay, so in the screen right now, this is actually the truss given to you in yesterday's example. Okay, this is truss. Okay, truss with two redundant. One redundant is come from. Okay, one redundant is come from reaction at the support. Reaction at the support AY. And another one redundant is come from member. So yesterday we have chosen FAD, member AD removed from the system, FAD. Okay, so these are the two redundant in the system. Okay, by having this, we have to remove AY. When we remove AY from A, the pin become roller. Pin become roller, and we also remove member. AD. We also remove member AD. So by removing these two redundant from the truss, we will get degree of indeterminacy is equivalent to 0. 0 means we have determinate truss, and in determinate truss we can be able to determine member forces, because in truss analysis what most important is member force, because we need the member forces to substitute into the displacement formula. Okay, so we have three systems. So we have actually calculated three systems. Okay, so this is the primary truss. So this is what we have calculated yesterday. Okay, this is the primary truss. So all member forces in this diagram, okay, in this truss is N0. N0 is always symbol for the primary system. N0, primary truss. Okay, and we have already calculated the member forces in redundant number 1. Redundant number 1 is redundant number 1 by looking at this. Okay, redundant number 1 is AY. Okay, this is redundant. This is redundant AY applied. Okay, this is redundant AY applied. Okay, in redundant AY applied, so remember that the truss, the truss is a system. The system must be balanced, means that it must be in equilibrium. Okay, it must be in equilibrium. Equilibrium at all time. Okay, at all time, externally. Okay, externally and internally. Externally actually referred to reaction. Externally actually referred to we calculate, we can have value of reaction whenever the system or the truss has external loading. External loading means that we will have the value of reaction at the support. Support in this truss is actually EX, EY and AX. and externally must be balanced. Means that if we only have one vertical force at A, no horizontal force at all, no horizontal external loading, no horizontal force at all, means that automatically there will be no reaction, no horizontal reaction at A and at E, because there's no value to be balanced. Okay, that is why we get AY. In this case, we get AX, not AY. AX is equivalent to 0. EX also equivalent to 0, because in this diagram, there is no horizontal forces in the system to be balanced. So automatically, if we calculate, we also get 0. So actually, by looking at the diagram, we will find that there will be no value for AX and EX, because there is no horizontal forces in this truss. Okay, that is why we will get AX 0, EX also 0. So what we have is only vertical reaction. Vertical reaction means that the system must be in equilibrium externally, and a unit value of AY, it is actually external system. Okay, reaction, we calculate reaction based on external force, external load. So when reaction is the redundant, means that a unit value of AY is external load. Okay, a unit value is external load. External load means that if in this system, in this truss, okay, there is a vertical force, means that okay, the vertical reaction must have value. Okay, must have value. So externally, to be balanced, we will have EY, which is equivalent to 1, because we need to balance a unit value of AY. Okay, that is why we have like this in the diagram. Okay, so to balance a unit value of AX, okay, we have EY, which is equivalent to 1. Okay, so now the system is externally equilibrium. Now after we have determined the externally equilibrium condition, we need to check the system internally. We have to check the system internally. Okay, we have to check the system internally, where we have to make sure that at each joint, okay, the total Fy, okay, internally means we need to check. Actually, externally also we do the same, but we just have to compare with all external loading and reaction. Okay, and for internal, okay, we have to check this. As well, but we need to check this joint by joint. That is why we name the method as joint method, because we need to check. We need to make sure that at each joint, okay, this criteria will be fulfilled. Okay, total Fx 0, total Fy 0. Okay, so in this truss, based on the reaction, because okay, in this case, since we have a unit value of redundant at A, okay, at A like this, automatically at A we need to balance a unit value 1. Okay, this is negative 1. We need to balance with positive 1. But we don't have horizontal value at A. That is why AB will become 0, because there is no horizontal force at A. There is no horizontal force at A, so automatically AB will equal to 0. Okay, AE we get from a unit value at A. So balance this with this, and then complete with this one, and this one must be balanced as well. So since the reaction EY is equivalent to 1, and this is also 1, means that, okay, we have another member, inclined member connected to E. Automatically EB will be equal to 0, because, okay, there will be no difference. Okay, it balanced already, so automatically BE is equal to 0. Same goes to ED, because from E there is no horizontal force, means that we don't need to balance anything for ED, so that is why it is 0. So we continue, we get, okay, DB 0, BC also 0, okay, and last one CD also 0, because there is no value to be balanced. So for truss, due to truss system, a redundant system, due to a unit value of AY, so we have this truss. Okay, we have this truss. Only one member has value. Only one member has value. Okay, it is AE. The rest are all 0. Okay, we move to the redundant number 2. We move to redundant number 2. So this is redundant. This is redundant FA. This is redundant FAD. Okay, this is redundant FAD. Okay, wait. Okay, this is redundant FAD applied. Redundant FAD applied means we have in this, okay, in the truss where the redundant is member force, automatically, because member force is actually internal forces. Member force is internal force. Member force is internal force. This is member force. FAD is member force. Member force. AD, okay, is member force. And member force is internal force. Internal force. Okay. Okay, member force is internal force. So by looking at this truss, okay, no reaction value at all, because we find that, okay, there is no horizontal reaction, external horizontal reaction, and there is no external vertical reaction. So automatically there will be no reaction value. So AX will be equal to 0. EX, okay, EX also equal to 0. And EY is equal to 0. So when we have truss subjected to a unit value of redundant, so what we need to have, okay, what we need to do is we will have values, okay, by values of member forces in one, okay, in this section only. Okay, in this section only. Okay, we will have the value in this section only. Always. Okay, always. Because Okay, A, B, C, and C, D, because when BC will have value whenever at C there is an external loading, but there is no value at C. Okay, there is no value at C, so at C this is 0, this is also 0. Okay, so automatically, okay, there is no loading, external loading, right? So all this is 0. Okay, all this is 0, so this is also 0. So all this will be 0. So this is also 0. This is also 0. So that is why we only have values, okay, in the, okay, what we call rectangle, rectangular, rectangular, rectangular or square section. Okay, in rectangular or square, depending on the geometry. Okay, rectangular or square section in the truss, depending on the geometry. So what we need to do is we need to start with balance. We need to start with balance. Balance by using the arrow. Balance using the arrow. Okay, of course we need to apply a unit value first, and positive FAD. Okay, positive FAD is in this direction. This is positive. Okay, positive. So that is why we need to, okay, we need to put a unit value like this. Okay, step number 1, okay, not balance but resolve. Okay, a unit value of FAD, we need to resolve in X and Y. Resolve in X and Y. That is why we get X and Y for a unit value of FAD. And after that, we need to balance. Balance the arrow. Balance the arrow. So, step number 1, we need to put a unit value of member force of FAD. And a unit value, since it is inclined member, we need to resolve in X and Y. We need to resolve in X and Y. And after that, we have to balance the arrow. Balance the arrow. So, we will put the arrow to balance everything in the rectangle. Okay, in the rectangle, we need to balance. So after we have put all arrow, means that everything balance, we need to determine the value of the horizontal value and the vertical value using trigonometry. Using trigonometry, we will determine X value, horizontal value, and vertical value. So in this case, okay, in this case we have 6y, 8 is, this is X, okay, 8 is X. So this triangular, okay, for the trigonometry, we will get 6, 6, 8, 10, 3, 4, 5, 6, 8, 10, 3, 4, 5. So 1 is equivalent to, so what we have is 1, because when we interpolate, okay, we will refer to two triangular. We will refer to two triangular. So we have two triangular like this. This is the concept of interpolation. We have 6, 8, 10. 6, we have 6, 8, 10. 6, 8, and 10. Okay? Fulfill 3, 4, 5 for trigonometry. And what we have? We have in another rectangular is 1. Okay? And X and Y. X and Y. So what we need to calculate is the value of X representing horizontal force value, the value for horizontal member, and Y is the value for vertical member. Okay, so having these two rectangular, okay, triangular, so we need to interpolate. Okay, so to do this interpolation, if 1 is equivalent to, terbalik. Okay, if 10 is equivalent to 1, 6 equivalent to 0.6, 8 is equivalent to 0.8. So that is why all the member forces which is horizontal, okay, the value is 0.8. Okay, the value is 0.8. And all vertical value, for vertical member, the value is 0.6. Okay, so this is the redundant system, where the redundant is come from member force. Okay, all this we need to substitute into the table, because what we want is summation. Okay, because what we want is summation. Okay, so we have R1 is equal to AY, and R2 is equal to FAD. This is AY. FAD. So we have, okay, delta 1 naught, delta 2 naught. So this is for the compatibility equation. Plus, okay, plus F11, F12, F21, F22 times with AY and FAD equal to 0, 0. Unless support settlement, if support settlement is given, then the value is no more 0. Okay, support settlement. Okay, now there is no, we don't need to consider support settlement, so the value is equal to 0. So by looking at this, we have 6 displacement. Okay, actually we don't need to write the displacement formula, because we need to actually adopt whatever we have learned previously under principle of virtual work, where we need to when we have to calculate displacement in truss, we need to have the member forces in two system. Okay, in two system. Okay, so in each of the, okay, the symbol of displacement, 6 displacement stated here. Okay, we can see that the notation, there are 2 notation. Okay, so we just have to refer to the notation to calculate the value. Means that if we want to calculate delta 1 naught, it is N1 N naught. Okay, if we want to calculate F1 N2, if we want to calculate F1 F12, it is summation N1 N2. We just need to follow AE times L. Okay, we just need to follow whatever notation that we use. Means that we don't have to write the formula for each of these. So by looking at this formula, this equation, the compatibility equation, we know that what we should have in the table. Okay, we know that what we should have in the table. So in the table, so we have to have the table, because what we want is the summation value. So in the table, of course, we want all this. 1 naught, 1 naught, 2 naught, F11, F21, F12, F22. And we know that for the formula, we need to time with L, we divide by AE. But AE is constant, so we don't need to have AE value. Okay, we don't need to have AE value, because AE value will be cancelled at the end of analysis. So what we should have in the table, okay, will be based on the notation that we use. Okay, the notation that we use means that in the table we should have the column for N1 and not L. We will have N2 and not L, we will have N1 square L. Okay, we will have N1. Okay, we will have N1 N2 L, N1. Okay, wait. When 1 and 2. Okay, N1 N2 L, we will have N2 square L. Okay, we depend on whatever notation that we have in the compatibility equation for the sixth displacement. So N1 N2 L, we have N2 square L. Okay, N2 square L. Okay, so to have the value of this means that we need to have the three member forces which come from three trusses. Okay, and 2 and 1